All right, Physics 2. Welcome back. We've got part 1 of Monday's lecture for week 14. We're going to start to jump into chapter 22, which is going to be on Faraday's law. But I wanted to start off today with a little example, just to start getting back into the terms of thinking in terms of magnetic fields and EMF. So, we have an airplane. And it's traveling at 1,000 kilometers per hour in a region where the magnetic field of the Earth is equal to 5 times 10 to the minus 5 Tesla. And it's nearly vertical. By that I mean the magnetic field is nearly vertical. So we've got our airplane traveling horizontally and the field is nearly vertical. What is the potential difference induced between the wingtips 70 meters apart? So we have a conducting metal object in the form of an airplane traveling with velocity through a magnetic field. That's right. We've got induced EMF. Motional EMF. Woo! But we know how to handle that one. So all right, so first we need to convert our velocity. So our velocity is 1,000 kilometers per hour. We need to get that into meters per second. So times 1,000 meters per 1 kilometer times 1 hour per 60 minutes times 1 minute per 60 seconds. Cancel that, cancel that. Cancel that, cancel that, cancel that. And we're left with the velocity is equal to 280 meters per second. And our velocity is perpendicular to our magnetic field, so we can use our nice little estimation. EMF is equal to BVL. And we got everything we need. EMF is equal to 5 times 10 to the minus 5 Tesla times 70 meters for the length times 280 meters per second for the velocity. EMF is approximately 1 volt. Cool, huh? All right, so now that we've refreshed our memories on how to look at induced EMFs and motional EMF from a magnetic field, we're ready to start digging into chapter 22 and Faraday's law. So we're going to be chugging right along with looking at Maxwell's equations. There we go. So leading up to this chapter, we have been treating E fields and B fields kind of separately, like they're separate. We've definitely seen that they're related, but if you recall, when we talked about the fundamental forces, we had the talk. And we said that electromagnetism is one force, which is 2 words. All right, so This is going to start to lay the groundwork to really understand what we mean by talking about them in terms of 1/4. And this is going to open up all kinds of doors in terms of how you can more deeply understand the physics of the universe. It's very cool. The foundations of optics are here, just the foundations of so many fundamental principles. So, all right. I'm getting off of that. And so what we're going to learn is we will learn that if there is a time-varying magnetic field, then there is also a curly electric field. See? That's right. We're going to see some curly electric fields. And we're going to learn about magnetic induction, which will be used to explain this phenomenon. And this is going to lead us all into Faraday's law. Okay, so this is what we have to look forward to. I imagine we are going to start this chapter and then finish it after the exam, because I want to take my time with it. All right, so starting off, let's talk about curly electric fields. And to do this, we need to return to our fond friend, the solenoid. So that's where you've got all these loops, and you've got a current running through it, and a magnetic field. All right, so we know how to describe the magnetic field in a solenoid. We can do it either using Biot-Savart if you really want to do some integration, or Ampere's law, which is beautifully simple. And we know that a solenoid with current I has a magnetic field of mu naught Ni over D, where N is the number of loops, I is the current, and D is the length. And inside the solenoid, B is pretty constant. As long as you're not too close to the ends. Okay, so, and the magnetic field outside is negligible. All right, so if I is constant, then B is constant in time. So if you have the same current the whole way through, then you're going to have the same magnetic field. This means that a charge outside of the solenoid will not experience an electric or magnetic forces from the solenoid, even if the charge is moving. However, this will all go out the window if you vary the magnetic field with time. Everything changes if dB dt is not 0. Because if dB dt is not 0, then the electric field outside is not 0. which means that if you have a charged particle going by that solenoid, it is going to experience the impact of this induced electric field from the time-varying magnetic field. So, the induced electric field is proportional to the rate of change at which this magnetic field is changing. So, let's take a look at what this looks like. And I'm going to need some room. Oh, and you need to see the bottom. So this induced electric field is proportional to the rate of change of the magnetic field with respect to time. Okay, so we have our solenoid. Here it is. Here's the middle. Here's the magnetic field. And we've got, the current. And we've got our electric field. Do that in orange. And this is coming from the variation with respect to time of the magnetic field. So, B is still approximately 0 outside the solenoid. This is true both if it's varying and not varying with respect to time. And if B is not varying with respect to time, then there isn't an electric field outside the solenoid. But if it is, if dB dt is not 0, so it is changing, then you get this E, which has a 1 over R relationship from the solenoid. And this field behaves just like any other electric field. So you can calculate the force using F is equal to Q times E. And as this field comes from something other than a stationary charge, it's called a non-Coulomb field. So this field stationary charge is called a non-Coulomb field. So, an ENC, you might say. Okay, so, and of course, we sort of hinted that we would get to curly electric fields earlier in the class, and here we are. Curly electric field. So let's talk about the non-Coulomb electric field. So, a Coulomb electric field is produced I think I am seriously dealing with my pen running out of ink. Oh boy. So it's just like a regular lecture when I have a marker run out of ink, okay? Let's switch over to blue. By the way, I got brand new pens as soon as I knew I was going online. So a Coulomb electric field is produced by charges according to Coulomb's law. So we know E is equal to 1 over 4 pi epsilon naught Q over R squared times R hat. So we're familiar with that. A non-Coulomb field is associated with a changing magnetic field. So that's dB dt is non-zero. And it is going to be proportional to the rate at which that magnetic field is changing with respect to time. So, and outside of a solenoid, it's proportional to 1 over R. So the further you are away from the solenoid, the more that electric field is going to drop off. Okay, so let's look at 4 different cases. So we've got our magnetic field here. It's coming out towards you. Then you would have your curly non-Coulomb electric field. So in this particular case, B1 is out and increasing, and minus dB dt is into the page. So we look at this with respect to the rate of change of the magnetic field, and there's a minus sign associated with it to this. Okay, so we could also have a situation. So notice which direction the non-Coulomb electric field is going around. So this direction of non-Coulomb electric field, when B1 is out of the page, is associated with a negative rate of change that is into the page. Now, if we put our non-Coulomb electric field going in the other direction, still with the magnetic field going out of the page, then that implies B1 is out, it's decreasing, so it's getting smaller, and minus dB dt is out of the page. So the electric field going around this way when the magnetic field is out of the page corresponds to a decreasing magnetic field, and the rate of change is going out of the page. Okay, so let's look at 2 different situations where the magnetic field is going into the page. So here we have a magnetic field going into the page. Our non-Coulomb electric field is going around counterclockwise. In this particular case, B1 is increasing, so the magnetic field is getting bigger, and so dB dt is out of the page. And now we could look at the reverse. Oops, I forgot to change colors. So now we have E and C going in the opposite direction with the magnetic field going into the page. And so this would imply B1 is increasing and minus dB dt is into the page. All right. These would be some charts I would recommend having on your sheet for the exam. They're very useful to just sort of internalize. So what I'm doing right now is I'm just laying down some groundwork. that we can use and some tools that we can use as we work towards understanding Faraday's law. So what we can see from this is that the rate of change of the magnetic field is determined by the non-Coulomb electric field. Okay, so building on that, the direction of the curly E field. So point your thumb in the direction of minus dB dt and curl around in the direction of E non-Coulomb. So let's test it out with the diagrams we just drew. So remember, it's the minus dB dt. So minus dB dt for this one out of the page correctly corresponds to that non-Coulomb electric field. dB dt into the page, turn. Minus dB dt out of the page, again, corresponds to the correct curling of the field. Minus dB dt into the page, curl corresponds to the correct direction of that curly electric field. So if you know the direction of minus dB dt, then you know the direction of the non-Coulomb curly electric field. Okay, so obviously that requires you to find the direction of minus dB dt. So this is how to think about that. So if you have a magnetic field, and so here's your magnetic field B, and then if delta B is in the same direction, then we can see B1 is going to be T plus delta T. This is increasing. And so, since B1 is increasing with respect to time, then we would have minus dB dt, delta B delta t is going in that direction because it's that minus sign that comes with it. Likewise, if you have your magnetic field, so you've got B1 and then your delta B with respect to time is here, then your dB dt minus is going in that direction. So basically, you want to draw B and find the direction of change. And remember, there's a negative sign. All right, so in terms of how to keep this straight, there's a couple of different things. I would really recommend using these diagrams to your advantage and to use a combination of the right-hand rule as well as a good sense of the different diagrams we have gone over to remember these concepts. And remember that when you do this for your exam, that you will get a sheet to draw some hints down. Please take advantage of that. All right. So I am going to pause this lecture here, and we'll resume next time talking about the impact that current has on how you can use a varying current to vary the magnetic field within a solenoid.